In the last video, we studied loops and conditionals. We found ourselves calculating the length of the program and the lengths of jumps. Let's write a program to calculate these differences for us. We copy the file from the last video. We remove the file size. And delete the old program text. We move an immediate number into register EAX, and we subtract another immediate number from it. The difference is in EAX, and we want to see that number. The plan is to move EAX to a buffer in memory and write the buffer to standard output. We move the address of the buffer into ECX, although we don't yet know the address. We move EAX into the buffer, although we see in the opcode column this /r, who knows what that means. We have a write syscall. A 32-bit integer has 4 bytes, so the count is 4. And we have a syscall exit. Where shall we put the output buffer? In past videos, we put a buffer at the end of the program after the syscall exit. Let's do that. Now about this /r, we need to talk about the ModRM byte. In the x86 instruction set, some instructions include a byte in a special form called ModRM. If present, the ModRM byte contains additional information about the instruction in 3 fields. The 2 highest bits of the ModRM byte are the mod field. In the mod field, we specify whether an operand, named something like RM8 or RM32, is a register or a memory location contained in a register, or some variation on that. The 3 lowest bits of the ModRM byte are the RM field, where we specify which register contains the RM8 or RM32 operand or the address of the operand in memory. The remaining 3 bits in the middle of the ModRM byte are the reg opcode field, where we specify another register, often an operand named R8 or R32 in the instruction mnemonic, or we provide a few more bits to further identify the instruction. Our instruction move RM32 R32 moves a 32-bit integer into a register or memory location from a register. The target is a memory location whose address is in ECX. That's written ECX in square brackets. I'm looking at the Intel Manual, Volume 2, Section 2.1.5. Table 2.2 contains 32-bit addressing forms. We look up this operand bracket ECX in the leftmost column of Table 2.2 and find that bracket ECX has mod field bits 00 and RM field bits 001. /r in the opcode column means the reg opcode field indicates which 32-bit register is operand R32. There is an entry R32/r in the leftmost column of Table 2.2, near the top. We find EAX in that row, and the associated 3 bits are 000. So 000 goes in the reg opcode field. I recolor the bits in groups of 4 and convert binary to hexadecimal for a ModRM byte of 01. 01 goes in the blank. I show the ModRM bits in the note column. We insert byte counts. The program segment starts at byte 54 of the file, and PV address is 54800408 in little endian. So the buffer, starting at byte 82 of the file, is at address 82800408. The program length is 86 minus 54 equals 32. We make the binary, and it doesn't work. This error is typical of machine language programming. I invite you to pause the video and try to answer what went wrong. You might want to look at the whole source file. There's a link in the description to a copy of the file. See the file named 4binq.dmp. So what went wrong? In the ELF header, the program segment is readable and executable, but not writable. We are trying to write into a buffer in a segment that is not writable. We add write permission, remake the binary, and it works. Or rather, we get 4 odd symbols instead of a segmentation fault. The output is in binary. In order to see it in plain text, we pipe the output into XXD. This output, E8FFFFFF, is the result of 54 minus 6C in little endian order, which looks strange, as even in little endian, each individual byte is big endian. We can put the whole result in big endian order by reversing the bytes with instruction bswap. Another little adjustment. Here before the syscall exit, we set EBX to 0 with a 5-byte move instruction. There is a 2-byte instruction that sets a register to 0. The exclusive OR of any single bit, either 0 or 1, with itself, is 0. The x86 instruction XOR applies the exclusive OR operation to pairs of bits from its operands. So if the same register is used for both operands, the result will be all 0, whatever the value before. XOR RM32 R32, opcode 31/R. Another byte ModRM. We look up EBX in the left column of table 2.2 and see that the mod bits are 1-1 and the RM bits are 0-1-1. We look up EBX in the R32/R row of table 2.2 and see that the reg opcode bits are 0-1-1. So the ModRM byte is 1101 1011, or DB. There are other opportunities to shrink the number of bytes in this program. For example, in the syscall write, register EDX is set to the same value as EAX. Instead of using a second instance of the same immediate number, we could copy one register to the other. But let's do that another time. There is a better way to allocate this output buffer. We don't need to write explicit bytes at the end of the program. Instead, we can enlarge the segment in the elf header by raising the value of p memsize above the value of p file size. Now there's a lot of room past the end of our program. Now instead of relying on XXD to convert binary output to text in ASCII, I would like us to write the text ourselves. Binary output has 8 bits of information per output byte, but each byte of an ASCII output stream has only 4 bits of information if we are writing hexadecimal numerals. We have a problem of converting from base 2 to the 8th to base 2 to the 4th. We could simply break each byte in half, but I want to implement a more general method of writing a string of numerals in a given base. The usual algorithm involves repeated division by the base. The sequence of remainders in this process is the sequence of numerals we want, listed from least to most significant. For example, 19 in base 2 is computed as follows. 19 divided by 2 is 9, remainder 1. 9 divided by 2 is 4, remainder 1. 4 divided by 2 is 2, remainder 0. 2 divided by 2 is 1, remainder 0. 1 divided by 2 is 0, remainder 1. 0 divided by 2 is 0, remainder 0. 0 divided by 2 is 0, remainder 0. We might as well stop after we get a quotient 0, but we can keep going to produce leading numerals 0 if we like. We rename the file to fortext.dmp. Here the difference of two integers is in register EAX. We remove the bswap and this instruction that copies EAX into the output buffer. The algorithm produces numerals from least to most significant, but they are written in order from most to least. There are many ways to deal with this. I set ECX to an address well within the huge space we allocated for an output buffer, and I will be decrementing ECX as we write numerals there. Then, after all the numerals are written into the output buffer, ECX will be pointing at the most significant numeral. That's the last numeral computed and the first to be written. I will keep count of the numerals in register EDI as we go. We write the number base in EBX. We set EDI to 0 by XOR. EDI has bits 111, so the ModRM byte is FF. There's an instruction div rm32, unsigned divide, that divides the combined contents of edx and eax by operand rm32 and leaves the quotient in eax and the remainder in edx. The number we want to divide is already in eax. edx is supposed to contain higher bits of that number, so they should be 0. edx has bits 0, 1, 0, so the ModRM byte is D2. Div rm32 has opcode F7/6. We are dividing by the base EBX with bits 0, 1, 1, so the mod bits are 1, 1 and the RM bits are 0, 1, 1. /6 stands for a ModRM byte with bits 1, 1, 0 in the reg opcode field. So the RM byte is 1, 1, 1, 1, 0, 0, 1, 1, or F3. After the div instruction, the remainder is in EDX, even in the lowest byte of EDX, known as DL, provided the base is reasonably small. We want to convert the number in DL into ASCII. The numerals 0 to 9 in ASCII run from hexadecimal 30 to 39, so we add 30 to DL. But letter A does not follow immediately after digit 9 in ASCII, so there's more to the conversion. We insert an adjustment to reach the letters, and a conditional jump to skip the adjustment in case our numeral is a digit. Each time through the loop, we decrement ECX and increment EDI. We move DL into memory at ECX. Bracket ECX has mod bits 00 and RM bits 001. DL has reg bits 010. Altogether 00, 010, 001, so the ModRM byte is hexadecimal 11. The quotient from the last div operation is still in EAX. If non-zero, there are more numerals to generate, and we jump back to label numeral. Else execution continues down the page. The count of bytes to put out in the syscall write is no longer a constant 4. We want to use the number in EDI, so we copy EDI to EDX. I see now that my notation is inconsistent. Let me fix that real quick. Also, I pasted in this jump instruction with the wrong length. We fill in the byte counts. The jump length is 6a minus 8.1, which is congruent to 16a minus 8.1 modulo 2 to the 8th equals E9. The program size is 9.8 minus 5.4 equals 4.4. We make the executable, and it works. Let's swap the numbers so we're computing 6c minus 5.4. Yes, 1.8. And only 2 numerals are printed, so we got that right. Let's compute 6c minus 6c. Yes, 0. We tested for 0 at the end of the loop, not the beginning, so we would see at least one numeral in this case. Let's go back to 6c minus 5.4, but change the output base to 10. How about base 2? We've been printing numbers. Let's try to print the program itself, 1 byte at a time. We blank out the program size, delete these 2 lines that compute a difference, restore the output number base to 16, insert a label num2buff for the routine that puts the numerals into the output buffer, move inside the routine this instruction that resets the output pointer, and invalidate byte counts. We keep the address of the byte to print in a register. EBP is available. We start a loop labeled byte. Right away we compare EBP to the stopping address and exit if we've reached the end. The num to buff routine expects a number in EAX. The high bytes of EAX should be 0. The low byte AL of EAX gets a byte from EBP. We advance EBP to the next byte. And after the syscall write, we jump back to byte. We fill in the byte counts. We might as well use this program we wrote to compute the jump back to label byte. It's from 99 to 5e. (5e minus 99) is congruent to C5 modulo 2 to the 8th. The forward jump to exit is from 66 to 99, that's 33. The program size is A2 minus 54 equals 4e. We make the executable, and segmentation fault. Looking at the program, I see that after EBX is used as a syscall parameter, it doesn't get reset to 16 for use as the number base. We move this instruction that sets EBX to the base inside the loop. This moves the byte label 5 bytes earlier to 5.9, and lengthens the back jump by 5 bytes to C0. Other counts are unchanged. And seg fault. Looking at the program, I see an error in this line. AL gets bracket EBP. I was careless with table 2.2. You can't use bracket EBP with mod bits 00. But you can use bracket ESI. Let's replace EBP by ESI. And we get a string of hexadecimal numerals. It's supposed to be the first few bytes of the program, BE54804008BB. Let's insert space between bytes. We put a space in the output buffer before any numerals. We augment the character count after the numerals of the byte are produced. Now the program is 4 bytes longer, as are the jumps forward to exit and backward to byte. There are 1 numeral bytes and 2 numeral bytes, but we want them all to be 2 numeral bytes with a leading 0 if needed. The algorithm should keep producing numerals until there are enough. The minimum number of numerals goes in EBP. Another conditional jump goes at the end of the numeral loop. If the numeral count in EDI is less than the minimum value in EBP, continue the algorithm by jumping to label numeral. I update the byte counts and the lengths, remake the executable, and run it. After a couple attempts, it works. The bytes have changed due to the new instruction. We enlarge the interval to begin at 00800408 and end at AF800408. We see not only the whole program, but also the elf header before it. Here's the elf magic number. So now we can do what xxd-p does, even inspect our program in memory as it runs. But the programming experience is kinda rough. We will address that in future videos.